Okay, my scientifically minded friends. Now, young and old, I don't care which side of the spectrum you're on, you have had some science or will be required to take science, specifically chemistry and physics and, that type of stuff. Well, let's talk about that. Let's go to the basics of everything. What is the difference between hot and cold molecules? I'm going to tell you right now, they do not know this. The top physicists in the world do not understand hot and cold. I'm not kidding you. Okay, I'm going to show you right now. The physicists don't understand what heat is. They don't understand what cold is. They don't understand what causes the two. It says microwaving water really isn't the same as heating it, and that is correct. Heating it is from a burner radiation forcing electrons in. That's what it's doing. It's pushing electrons in. Now, microwave is shaking the electrons back and forth so that it's not pushing, they're just bouncing back and forth and getting hot inside very quickly. This is pushing electrons in, and that forces them to make a big mess of all the particles that are in here, and it gets heavier, believe it or not. Everybody says heat rises, yes, but that's because it gets into air, which is expansive. If it is just within the matter itself, like if you put a brick on here and heated it, the brick would get heavier. It's electrons. They are actually electrons, and that is the dipole electron flood theory. All particles there is are made of this one particular two-part, what we would always call an electron. We never knew that there was a black side to it, but there is a white and a black side. But the white is the pushy side. It's called the electron neutrino and the muon neutrino. And the electron neutrino, it pushes like crazy and causes heat. And that is what we're picking up as heat, is the push and shove of electron to electron. Okay, my contention is that everything there is made of electrons. An electron is really made of two parts, not just the one tiny little negative particle. They call them neutrinos. And one part is the electron neutrino, which is the part we always knew about. It pushes things, it makes things heat up and so forth. But it also has a muon attached to it, which is the black dark matter they've been looking for forever. It consists of 90+% of the universe. They never knew where it was. It's attached to everything that's here. Every white particle that bounces that we can see, it gives off energy, is attached to one of these black particles. And we actually saw them and separated them. Here they are right here. This is what a molecule, a photon looks like. That's the photon. Half of it is an electron. When you glue two of them together, which is nothing more than two little bar magnets. It's nothing more than two little tiny bar magnets. They have a weight. It's very, very tiny. But that's all there is that makes up everything there is these particles here. Now, this little glowy one has a field around it that says, I won't let any other glowy one get next to me. The black ones, yeah, I can have as many black ones as I want, but no other glowy one will get next to me. There's a law about pushing two particles together. They never, ever can touch. They can't touch. Now, we forced them to touch, which created this right here. We forced them to collide into each other's fields, forcing the fields to just literally explode. Right here, this should be almost unlimited amount of heat, but instantaneously it comes back to the black particle and they just come back to light. So right here, if we could harvest what's in there, I think we can get free energy. Because there's no increase, we didn't do anything whatsoever other than funnel this into a venturi, which splits the particles in half. I will show you that in a second. And then, of course, we saw the Higgs fields. These are the Higgs fields. And this is coming out right in here. This is pure raw energy. And then all of a sudden they reconcuss and create the Higgs fields. That they always call those the God particles. And this is blue. And blue is coming in real hot here and slowing down. And its light spins. It spins. Now, I just worked with light, so it was very desktop, very simple. Now, this is from CERN and Fermilab, showing the same particles I show, only they show them when they smash head-on protons and break them up into little pieces. And then they see these are the tiniest particles we've seen, which I agree with that, because they are part of light. All right, there's the black one, which is fixed. And this is right from Fermilab. This is not my diagram here. Now, this is, though, our light research, where we put light, a regular particle of light, well, a pulse red laser, through a venturi, and we could see these particles show up. Now, that is a photon. But then when it went through the venturi, it crushed itself so violently that the black separated from the white. And here we have raw white energy, and I mean it is extremely energetic. I mean, you can see the increase in energy. Just it has to be more energetic than where it was here. That's an increase in energy passively. We didn't do anything whatsoever here other than have a venturi. There's no added energy here whatsoever. It created its own energy by smashing its fields together. And there is a law. Let me show you that. Right, before we see that, I just want to show you, this is the particle literally fission, and that is literally fusion. In between is raw energy, and it's precisely identical to what CERN and Fermilab see, and they call the muon neutrino and electron neutrino, which is the black and the white ball. And then when they hit something, which is in Cherenkov radiation, they hit a different medium, which is this medium where they crush together. Here, they're hitting a denser medium, which is like heavy water, and there's many more electrons in it, so it pushes back and forces this separation for an instant there, and they absorb the high energy particles, basically. That's what it's all about. But these two are the same two particles we had, and here's the showers, and here's the muon by itself. That's what now they're calling it a sterile muon. It's sterile, it's all by itself. Now, that is precisely identical to what we see here, and then we see it separate. We see the glowy part, which is that Don Lincoln at Fermilab calls that a point particle. And that's, if you want to go back and look at it, look up his article from 2013. It's called What's the Point? Don Lincoln Fermilab. And this is from that article. As he said, this is a fixed particle. It never changes. It stays the same size, and it has a glowy little border around it, and that's it. And then this one, and it's dense. This one here has no mass possibly at all. And I can agree with that, because when you see an atomic bomb go off, the first thing that hits way off a mile away is a house just sits there and burns. It just literally burns. And then all of a sudden, because that's the one that's hitting it, it's not pushing it, so there's almost no mass there at all that I can tell. And then the next thing that happens, pew, the house goes flying. That is that particle coming and hitting. Two separate particles, and the reason is the white one always, forever always will surround the dark particles. And I could prove every word I'm saying. Okay, when I say I can prove everything I say, I never make a statement that there's no physical support for. Where's my physical support for two different particles? A real burny one and a real smasher one, which I showed you. This, the black is the smasher, the red is the burny one. Well, watch what happens in a nuclear explosion. This is the house that they test to see how it gets knocked down. This is going to be in slow motion. This is Atom Central. That's the people that put this up. It's called Teapot Apple II Q House's Atomic Bomb Effects. Now, let's even cut the playback speed a little slower, 25%. It's already at slow motion, so you may not notice what is going to happen here if it wasn't in slow motion. But in slow motion, it becomes extremely obvious. Here is what was sitting on the tarmac before they exploded it. It's an atomic bomb. And what does an atomic bomb consist of? A bazillion extra electrons. So many that it wants to fall apart right now. They don't want to even be stuck together as they are. they're decaying right in front of your face. It's because there's just too many stuck together. They don't want to be that way. Then they plate it with something and explode it inward to crush all those particles, and they bounce out. And what bounces out is the white ones. And the black ones, though, are going to follow them, but they're not in the front. The white ones everything is coated with white. Everything you see here is coated with electrons. 100%. 100% of everything here is completely surrounded by the glowy white ones. That's why you can see it. Now, what happens here if the glowy white ones hit this house? Will that show us what the glowy white ones are constructed of? I think it will. And I think it's exactly what Don Lincoln says. It may not have any mass whatsoever, but it has a hell of a lot of energy. Now watch. All right, let me open this up. Now I want you to confront your teachers and your professors and your scientists and physics and all that, because they have to take this into consideration to ever be able to teach you anything. Now watch what happens. Here goes. Way back here, boom. All right, it's going to take a while before the particles come. Bam! Look, what do we see in here? Just a haze. A haze of what? A haze of electrons. The white part, not the black part, just the white part. You don't see the house moving. I'm going to hit it and start it back up again. Watch. You don't see the house moving. Look at what happens. The house just burns. Totally burns. Let me turn the sound on because it goes like that. Okay, here goes. Now, there's nothing moved yet. Every single thing that was hit with electrons is glowing and burning. It just burned. No, nobody's even moved. Nobody's moved an inch. It's just coming up, vaporizing. There's no mass. There is no mass. It's just energy. I can't explain it. Okay, now watch. Now, all of a sudden, pretty much all the white ones have burnt off everything, and the black ones are going to be coming from behind because they're a little slower. And when it hits, boom, what do you see here? No more burning. Everything goes because these gigantic black balls are smacking everything out of the way. Before, you just had a little glowy. No, watch what happens now. Everything you should think would just keep going. It does not. It turns around and comes back. And why would that happen, Roger? Well, here's why. Because when this thing went off, the white ones are the ones that went. Every single one of them went, basically. Every single one, basically. The black ones followed, but then there was still a chunk of blackness there with no electrons. So he wants to pull them back. They have to come back. Now, not all of it will come back, but quite a bit does. Watch. Again, it's going that way now. Watch what happens. You see it turn around? You see what happens now? It didn't just keep going. It's coming back. And here it comes. All right? That's my proof. You see this? They're always talking about black holes. Well, they're right. There are black holes, and the white particles surround them. Let me show you how they did it in space, the Russians. All right. I have to give credit where credit's due. The Russians created this black hole in space, in their space station, in a vacuum chamber, and they injected charged particles. Charged particles push each other away. They don't, but they collect on the black hole. And here they are collecting. In the video it goes, I don't know, 6 or 7 minutes. I should show you. When they inject them in here, they swarm all around like this, and then they start to congeal, pushing the black matter to the center, because that's what electron flood theory says will happen. And it does. This is exactly what happens with everything. Now, on Earth, because of gravity, you don't get a hole like this. It's a little different because of the gravity. This is the only happens because it's in space. Now, what they had expected to happen was a lattice, which every charged particle would be a certain distance from every other charged particle. So it would create a lattice, up and down, all into a cube, like the whole thing would fill up with lines of particles. That's what they had expected. And then they got this, and then they freaked out. In this same set of experiments they did up in this vacuum chamber. A vacuum means there's no particles whatsoever inside this chamber. No particles. Then they injected these particles. And see the little glowy ones? Well, why is it glowing? Why would a particle glow? It's what's called plasma ionization. It's an extra electron attached to a micron-sized dust particle. So you have these tiny little, tiny dust particles, and they have an extra electron. So they glow because they're energetic. And then when they let them in here, they came in a stream. I'm going to do another video showing their entire video, because then they show convection. The convection where everything's going around and leaving a core in a sensor. Absolutely fabulous. And the only way you can do it is in zero gravity. And that's what they have here, is zero gravity. Now, you see the flatness of this circle? If this box had been perfectly symmetrical, or was a sphere, let's say, that would be a perfect circle. The reason it's flattened out is because there's particles up here and particles down here that are closer than the particles on the ends. So they're pushing more into the center, flattening that disk. Alright, this is mainstream. What is heat? Where does it come from? Heat can be envisioned as a total amount of energy resulting from the molecular motion of a substance. Not too far from correct. Heat can be envisioned as flowing from places where there is a lot of it to places where there is relatively little. Well, what is of it? What is it? Just as water flows downhill under the influence of gravity and molecules tend to move from areas of higher concentration, particle density, to areas of lower concentration. All right, so they are saying heat is particles. No disagreement whatsoever. Heat is usually given in joules in the international system, and it's equal to 4.18 calories, the amount of heat required to raise the temperature of a gram of water by 1 degree. And I've done all this stuff, so I'm going to show you I know what I'm talking about as far as this stuff goes. Heating matter causes particles in that matter to speed up, absolutely, because you're forcing electrons in. Cooling matter causes the particles to slow down.
Need cash to make a purchase? No worries. Payback checking refunds other...
Well, that won't happen again. That's what they have, a zzz on-off switch for the volume. That case is closed. I tell you, you can't get away from the ads now. Sometimes, and they slaughter my stuff with ads. I have nothing to do with that. Anyway, particle movements and definitions. All right, temperature is theoretically limitless quantity at high end, but its value can be no lower than 0 Kelvin, which is equal to a temperature known as absolute zero. And what that means is there's absolutely zero extra electrons. Every time you add an electron into something, it creates more and more temperature, and it gets heavier and heavier and heavier, and it gets warmer and warmer and warmer. Every particle you put in is pushing and shoving other particles. That's just the way it is. And if you take every single extra one out, you end up with 0 Kelvin. There's none left to go. Vibration is impossible. It's impossible to vibrate anymore. There's nothing pushing, nothing shoving, which is the white particles. They push and shove. They're gone. Now, I'm working on heat because this is still a little bit of a gray area. But anyway, the average kinetic energy of molecules in a sample, be it solid, liquid, or gas, is used to establish temperature because this value is stable at a given temperature. Now, something you want to understand is weights and measures. I dealt with weights and measures, and I had weights that had to be calibrated to a very, very specific weight. And in order to make them standardized, they had to go to the Weights and Measures Department, Hartford, Connecticut, where they put them on this special thing that tested them how much they weigh according to their standard weight. And it had to be exact. And I brought them up there when they were cold to be tested, make sure they were exact. And the guy said, you have to leave them overnight. And I sort of wondered why. And I said, why can't you just test them now? You're not doing anything. No, I don't think I said that, but he said, no, you have to leave them. They have to be the same temperature as the room. And which is just, all it means is it's not trying to give any electrons out and not trying to take any in. Because the electrons have weight. He said they won't weigh right. And I was always sort of a little skeptical about that, but I did a lot of work in this area. I'll show you well, here it is right here. I was going to show you this. I did this. I tested hot and cold and the temperature in the mixture and all these different solutions and how the heat of reaction, the heat of solution, and how all the calculations regarding how the temperatures dissipated depending upon whether it was acid or a salt, which means has extra electrons or not extra electrons, and then all this, I can't even remember what it was. This is 50 years ago. And but it always came out in electricity. It was always electricity. All electric power, all power. Every single bit of power is electric. I don't care what it is. When wind hits a propeller to turn a generator, that's electricity. That's electric electrons bashing into other electric electrons. White to white pushes. Okay, bang. Push me, I push you. Push to shove. And it makes a propeller shoved and spinning around. And that forces the generator that's attached to the propeller to force its way through all these magnetic fields. And those magnetic fields are just exactly like this. All right, these are all magnets that surround. Well, I have one opened up. Hold on. All right, here's the deal. This is a DC motor, direct current. All right, you see inside there? Those are magnets. And as this thing spins, the magnetic influence into this iron core forces these coils of wire to do just like a Tesla coil does. It builds a field. And then it discharges that field out through these little splits. I don't know if you see that. And these brushes, this is what they call a brush box, surrounds those, and as it turns, it sends out plus, minus, that type of thing. Now, so this is being spun, just like this one, wherever I put it. I'm terrible. I put something down that's gone. I mean gone. Well, it's historical data at this point. Now, but this spins, and you can see, if you could feel this, it click, 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 click. And if I spun this, like that with my fingers, I can put electricity out through here. That's a generator. If I put electricity in there, it spins a motor. It's just exactly opposite. That's what a generator is. And we can, it's pretty well understood now with electron flood theory. It's not understood whatsoever. Once you step into the realm of Bohr model, it doesn't work. It absolutely doesn't work. It never worked. And as a matter of fact, here, I'm going to show you what I did. This is 50 years ago. All right, I've shown this many, many times, but people want to see some validity that I have some right to be speaking in this room. And trust me, I do. All right, this was all stuff about heat and light and energy and chemistry and bonding and resonance and all of this stuff. All about, these are all theories and so forth. And I was trying to prove them out. I didn't just accept them. I tried to prove them out. And I came up with the fact that there was nothing but dipoles. There was nothing but dipoles. Everything was magnetic, the magnetic properties. And there was two types of energies, dipole to dipole, push to shove. Transfer of energy is from light to atomic vapor. Atomic vapor is those little particles I showed you. And I went through everything. I mean, I went right down the line. You want to see what I did, and this is just what I had for my notes. I mean, I did a lot of other stuff too. But this was after I got out of the Army. I was in Nike Hercules missiles when I was in the Army, working on the missile sites up in Alaska. So I have a good background to speak in this. Most of the people that are are telling you what they know about quantum have just heard it from somebody like, well, I'll show you how they hear it. Okay, this is pretty much what happens with quantum physics. Now, this is Yale, and I went through their quantum course with this guy. He's a nice guy, and he's just honest. He's just being honest. Nobody at this point in 2011 understood anything really about quantum physics. I mean, a total mystery. And it has been up until electron flood theory, because it's still a mystery. They have no idea. There's no accounting for gravity, dark matter, any of that stuff. Now listen to what he has to say, because this is just reality. It's truth.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal.
All right, I'm just going to, his goal is to tell them what he's heard, basically, and to sort of try to think of how it could work. And it never, like he said, it's not intuitive. It doesn't work. It just doesn't work. You can't have one just gigantic proton in the center and have one little tiny electron out here. It doesn't work as a hydrogen. Absolutely not. Because hydrogen blows up like you just wouldn't believe. Now, hydrogen is nothing more than this. It's a ball of electrons, and there's so many in this, it becomes stable at a certain point, and it says, nope, that's it, no more comes in. And it says, I'd like to get in there. It says, no, you can stay right out there. We're going to call that your quantum distance. And if somebody else leaves, you can come in. And boop. Sometimes there's extra. They call them isotopes. They somehow got in there extra, and eventually they'll leave. That's called nuclear decay. That means there's extra ones, and they want to get rid of them, and it'll drop one off. And when they're really torn up, then you have radioactive decay, and boom, these big pieces go flying away trying to get stable. Now, I talked about using extreme amounts of resonance frequency to vibrate these particles back into their stable condition, to remediate the nuclear wastes. I think that's possible. I really honestly do, because I showed it in the salt experiments, and I'm going to show you again the salt experiments, and I'm going to show you the other ones where I can show how this is nothing more than a dipole core which will attract a certain number of electrons outside, and they will be stuck right in there because they want to get in and they want to push away. It's push to shove, and boom, they lock in. I'll show you that, and that's in what's called tractor beam magnets. If you looked up salt table experiments and tractor beam magnet experiments, you're going to see those are the two things that show the structure, which is the salt beam one, shows the structure of the core, and then the tractor beam one shows how the actual interaction works, and it holds on tightly. Well, they're semi-tight, but that's why they can bounce away. They used to call it string theory. I call it spring theory. They're just like on bouncers. So there's normally one out here, let's say, and it's exactly 5 angstrom units away, let's say. Well, when there's a lot of interaction going on, it could go down to 4, it could go up to 6, it can push and shove and bounce around here. That is going to cause heat, yes, absolutely. Push to shove causes heat. But it's not because it's just jiggling back and forth here. In the microwave, yes, that is exactly what happens in the microwave. They just jiggle and heat like hell, pushing and shoving each other around. It doesn't add any electrons, I don't think. It might. I'm not sure. I don't think some of them have to try to weigh the cold versus the hot and see if it adds electrons. If it adds electrons, it's going to weigh more. I don't know how you'd actually weigh that, but when you see the experiments, you'll see that it's pretty obvious that these are what can fly off of here. And when another particle comes in and hits this, boom, this just bounces it away, and that's what we see as light coming back. All right, so we never see the dark stuff, which is deep inside the core. There's going to be a dark inside. By the way, he is a nice guy. He really is. I don't mean to belittle him whatsoever. He's just doing his job. Nobody knew anything about this. But now it's time to pay attention. I've tried to contact him. I've never gotten any response. So at this point, I'm losing a little respect there, my good friend. But I understand your position. Now, and I looked at some of this, and some of it makes sense, some of it doesn't. He's trying to do the best he can with what he's got, and he doesn't have anything to work with because it's just wrong. How can you make something out of something that's wrong? All you could do is talk around and dance. And hand out diplomas to people to dance the same dance you're dancing. And if they don't, you fail them. You say they're stupid, they couldn't understand. Now, when he talked about Feynman, I fully understand the Feynman diagrams. It's very simple. All right, this is exactly what we did. This is a Feynman diagram. Now, it says the diagram illustrated above represents the interaction of two electrons. To me, an electron is a black ball and a white ball together. Each electron is represented by a straight line which exchange a virtual photon and then repel one another. Yes, they crash in together as a photon, actually, and split off as the muon neutrino and the electron neutrino. He's got it like 90% of the way there. And he's showing that fermions, they're the energetic particles, are these particles, and then when they energize and smash, these are the photons. That, you know, it's hard to say how he's showing whether the photon is coming out this way, coming out this way. I'm not sure how he's relating the wave, which is the particle, spinning particle. He's calling it usually gluons. Yes, that's the four particles that are glued together. And then the Higgs come out in along with these. I don't know, he's not showing them there. But anyway, basically, this is the same thing that we show. The field of the particle box comes in, smashes, and falls apart and splits. And nobody can explain that because they don't understand it's made of two particles. Every light particle is made of two particles. All right, this is exactly what I'm talking about. It's called tractor beam magnets. And here's what's going to happen, is he's creating the core of a nucleus, okay? Which means he's going to make a negative center, or I mean he's going to make the black portion in the center and the white portions on the outside. And he's going to do it by just reversing the magnets. So we have the negatives, basically we would think of on the outside, and the positive on the inside. Watch what happens. This is Latham's crazy machines. Very, very good. And this goes back to 2014. So this is like 8 years ago. Now watch this. All right. Now he's got all those magnets on the outside. He takes another one that tries to attract to it. He turns it upside down and puts it in here. So now, what does he have? He has a positive center and a whole bunch of negatives. Now, what's he going to do now? He's going to introduce another negative. What does that mean? This negative now will want to get to this positive core. And that's what gravity is. That's what all molecules want, to attract enough electrons where they become stable. This thing is basically unstable right now. It has no electrons surrounding it to protect it. So this one comes up and it says, hey, I want to come in. It says, well, you can't come all the way in. I know you want to get to me, but you have to stay out here. And watch what happens. Because this is now, boom, there it is. That is exactly identical to quantum theory. Now, where is it being held? Between the fields of these two magnets, its field is interacting and locked into this central groove right in here. It's in a cavity. And he could shake it, and you'll see what he does with it. Now, right now, that's just ambient temperature. That's like me taking this rock, I'm just moving it around in the air. It's not going to get hot. It's not going to get cold. You could fan it and push some of the electrons off it, and it would get a little cooler. Yes, absolutely. But it's not going to change a whole lot. When you force electricity into something, or you scrub the hell out of it, it will push and shove all the electrons. Yes, and he's going to do that in a second. And then eventually that thing will go flying off of there. And what is that? That is heat moving out of an area that is saturated with electrons, and they're pushing so hard it has to leave. Where does it leave? It goes into the gases that surround it. The gases absorb it as an extra electron, but then it dissipates quickly. All right. In here, there's just so many of them. When he starts shaking it, it represents the fact that there's just a ton of extra electrons. Watch. He's moving it around. It's just barely moving. No big deal. That thing will stay there forever. It's never going to go away from there. Now we're going to heat it. We're going to put it in a hot plate. It's getting a little hotter, getting a little hotter. We're going to turn up the heat. A little hotter, a little hotter. Whoa, baby, you're ready to go. Bang, gone. Now, it leaves as light or it leaves as heat, some form of radiation, but it is that particle itself that leaves. Too many of them there at the same time. All right, here's another one. This is by Action Lab Shorts. These guys are good, Action Lab. Now, he's talking about running a Dremel with a magnet, a very strong. These are those neodymium magnets. They are strong. And he's going to be running that Dremel, and this other magnet wants to, normally it will go snap right up into that magnet and they'd be held together. But when he spins this, it goes push, pull, push, pull, push, pull, push, pull. So it's always changing its field back and forth. So it pushes it away and it attracts it. Push, attract, push, attract. So it actually hovers here. Watch.
If you glue a magnet to a Dremel with the poles pointed in this direction, you can actually get a magnet to lock in place in midair. I looked it up, look. It's locked in place. Let's see if I can turn it sideways. No way.
All right, do you understand what's going on? This is nothing more than plus, minus, plus, minus, plus, minus, and it's spinning like crazy. So what is that doing to this? Push and pull, push, pull, push, pull, push, pull, and there it is. The faster you spin that, I imagine the closer the contact would be. But I would think, yeah, the faster you would spin it, the closer it would come. And I think I might even be able to show that when he first starts off. All right, here he goes. I think I heard it spin up. Listen.
To get a magnet to lock in place in midair. I looked it up, look.
You hear it goes
it's
faster?
It's locked in place. Let's see if I can turn it sideways. No way.
Yeah, I'm hearing it going faster.
From far away, the attractive force dominates, but as it gets really close, the repulsive force starts to dominate. And so they balance each other out at some stable equilibrium point that locks the magnet in place. Now you can show this effect in a much more precise way by using a rotating drum that has magnets in it. These videos are from a man named Hamdi Yukar. He basically has devoted the last 5 years of his life in studying this effect. What's really interesting about this is it's not very well known in literature, and he wrote a really good research paper documenting his entire research in the field and mathematically proving how the effect works, showing the different frequencies that you need. To my knowledge, it's the only paper that...
Okay, and that could well be, but does he understand the dipole nature of the particles that construct everything? That's where you have to start, and I don't know if he does. I'd love to engage. Now, you should come back here and look at this. New science requires a non-academic university, which we are going to create, and I need help, I need support, I need people that are really interested in volunteering, experts that have mainstream knowledge that I can discuss back and forth. We need somebody to coordinate it. We need classroom presence online, questions and answers, and at some point this will become a very, very valid university because we're the only one that's able to transition into reality. The rest of them are scared to do it. They can't. So we are going to do this, and instead of going back again, I'm going to show you what the new science requires and about these particles instead of making a whole nother video about it. Now, rather than add another segment, I'm just going to go over the one I put up here. I believe it was yesterday. I'm going to beat this thing like beating a dead horse until it gets up and starts running and working on its own. Because it's time that it has to be addressed. I mean, I showed all of these things. Fermilab shows exactly the same particles. They say the muon, electron, neutrinos, we did it. That's fission, that's fusion. This is not a joke. This is all actual physical evidence to prove what I'm saying and support exactly what they say. Well, I didn't need gigantic colliders. We crushed light. We crushed the fields. All that is, you have to crush a field against a field, and they will carry them off of each other, like the Feynman diagrams show. Very, very unnatural to have them actually hit and split, apparently. But we did it, and we can do it all day long because we funneled them into a Venturi. Now, let me just play this. Listen. To ignore this, and then of course the government agencies to outright say we're not going to look at anything you present. Well, let me go back. Not protons. So we don't. All right, let me just pick it up right here. This is where I'm going to start to show the particles as they build molecules. Exactly what the Fermilab wants to see. That's the particles. Those are the particles right there. I mean, you can't miss this. It cannot be missed. And I've shown every single possible way you can show this. And we started from light, not protons. So we don't have all kinds of debris. Now let's go back and look. All they're looking at is trash. Particles. We're looking at the exact particles. This is so beyond cool, it's amazing. You can see we have a core. That would be... Here, you know what I'm going to do? Let me just re-explain it. The nucleus of the first row, hydrogen or helium. Because that nucleus can only have a maximum of 4 surrounding electrons. This is what they claim. And I can agree with that. All right. All that means is this is a small quantity of electrons in a ball. And they seem to become stable at certain frequencies. I don't know what determines that frequency. I cannot tell you why a hydrogen is down here at 1839 or so particles, and a helium is up here at 7,352 or something like that. And then when you get up into plutonium and all that stuff, you got hundreds of thousands of particles in a ball, but still stable. The only thing is, they get more or less and less stable as they get bigger and bigger and bigger. Hydrogen is the exception to that. Hydrogen is extremely unstable. Helium is very stable. Lithium is unstable. This whole row, all down in here, is very unstable. And that's why we're going to see the calcium, the sodium and the chlorine, NaCl, is a polar molecule. That's why it shakes. Now, that's why we're seeing these patterns. I agree with that. There's 4 of them that want to get in, but they can't. And I'm going to show you another one with tractor beam magnets, just show you exactly how that works. I already showed you that. Now, what happens after you go through the first 2? You go into what they call the rule of 8. And instead of only... All right, here it is right here. Out here, that want to get in... Let me put it this way. You should come back and watch this. What happens is this table just goes zzz, boom, and all of a sudden, at this specific hertz, which is cycles per second, 1033, it shakes these up and down at that, and so they push and they shove. Now, I show, you see these areas here? These are areas that are pushing and shoving to push each other little particle away. I'm pretty well understanding this now. And the bigger you get, look at how elegant they get. Whoops. I'm not looking at her saying elegant. Hold on one second. All right, here it is right there. They just keep getting bigger and bigger and bigger. But they get more and more unstable, really. But the interactions between molecules can become so incredible. That's how you get all of these different types of molecules. But there's not just a certain, copper has like, 29 protons or something. No, it has tens of thousands of little electrons. And that gives it the ability to do all its molecular interactions. Copper is extremely interesting. When you hit a magnet against copper, it's like pushing it into a pillow. Watch this. All right, what you're going to see is an extremely strong neodymium magnet forcing itself to try to concuss with a big heavy-duty copper plate. Now, copper is right in here. These are the transition metals. Somehow, for some reason, it is completely saturated with fields of electrons around it that are just amazingly large. And that's why copper is used for conduction. There's just a ton of extra electrons. Now, I can't explain that specifically yet, but watch what happens. This is magnetic flux. Watch what he does, and watch the response to the magnet. Boom. It doesn't hit. It can't hit. You see that? It won't slide down. Normally that would just going right off. You see that? It's literally going through a dense flow of liquids. Look, boom. It should just go bang, but it doesn't. See that? The only possibility is that there's extreme cloud of electrons because it's push to shove. This is pushing or shoving back. No other explanation. Electron flood theory is literally the only possibility for the things we see. And this is, and I think I made a very, very good case for it, but that's just my way of thinking, although I think my way of thinking is right. All right, I love you all. Present this to your physicist friends, to your professors, to your teachers, to your parents, to your kids. See what they think. Talk about it. This is reality. This is not just some fluffy little thing. This is, before you can understand anything at all about matter, you have to understand how these little tiny particles interact with each other. So we got a lot of work to do.